I don't drink coffee. At home, drink tea. And of course I put milk in my tea. What kind of a savage do you think I am? All right, cool. How many images to play with? Let's steal that one. Yeah, that'll do. Okay. Yeah, compound data. That's this lecture. We have another couple minutes before we get going. Is YouTube working yet? All right. FP. Oh, I see. Someone's being funny. Oh, don't need functions 2. Up there we need. Anyone got any compound data related questions they want to hit me with? Before we get going. Ah, yeah, we'll do one of those. Spell with a K, by the way. I've got one over here, ready to roll. Very short, but I extended the timer, so hopefully we don't have such lag issues. Just to warm us up. Maybe we'll get going on that for you early birds. 3 questions, 60, 60, and 90 seconds each. Friendly nicknames, yes please. Bang, hit the table. All right. Go away music. Okay, we've got some questions to get us started. Some things to get us thinking in the right frame of mind for compound data. If you use an array as a function, there is a way toad the array without changing the actual array. No, not possible. And that's next week's topic, reference semantics. It's good that you've noticed that. It's an important distinction with compound data. It's the primary difference between the trickiest, most notable difference between compound data and just what we would call atomic data, the data we've been working with so far. And you'll probably notice I keep switching between data and data. I don't know why I do that. I just can't pick which one's the right way to say it. Do we have any fun? We've got a zanier kid at this time. Still don't see any emus. Yeah, they are data. Maybe I just don't want to restrict myself to one or the other. Don't want to miss out. I appreciate that joke. The assignment 2 discussion session came and went with Kim last week. So everything's got to be done through the forum now. Yeah, it does depend on the country and the accent. I should know which one is my accent, right? But it's just one of those words that I don't think has a dominant pronunciation in Australia. Okay. The other one I always do differently depending on what mood I'm in is research or research. Well, yes, it's very on how to pronounce Australia is obvious and known to everybody. I don't often slip into some of the pronunciation of that word. Let's go. Ching. A slot in memory is, here's some statements about the size of a slot in memory. Slot in memory is a variable, remember? Anytime we declare a variable, we are making the program set aside another slot in memory for us, and then we're going to use it later on. Looks like we didn't need quite that long to answer this question, but at least we won't leave anybody out. Nice. For now, we'll see if the stream stays good. There we go. Always the same size. A lot of people said whatever size we ask for, which is actually, it can be an okay answer, but what I mean and what I want us to start thinking about is that the machine, the computer, it only has, it's stuck with a certain amount of memory space that it thinks of as a memory, as a slot. You can sometimes ask for more than one slot, but that's separate to the, like if you need more space than one slot has, you don't ask for a bigger slot. You ask for more than one slot. And so that's what's happening when we do arrays. We're not asking for a slot that's giant. We're asking for, say, 100 slots to be set aside for us. So the slots are really always the same size. And that's what causes the interesting behavior in compound data. They're definitely not infinitely big. The memory is infinitely big in our brains, but not infinitely big in reality, and definitely not zero. As I say, for arrays, you're asking for multiple slots, not for a larger slot. Okay. I don't like any of those names. Come on, someone with a better name, get up the leaderboard. Next. So how big is a memory slot? You might not even know what these words mean. Bits, but we'll take a guess anyway. For those who don't know, a bit is just a binary value 0 or 1. It's either on or off. And you can make, when you combine individual bits, you can put more than just, I mean, on or off is only enough to store true or false. So if you ever want to store more than just a Boolean, you're going to need more than one bit. Now, computers never operate on the level of 1 bit at a time because we've got gigabits, multiple terabits in our computers these days. Instead, they're operating on them in larger chunks. And it gets quite complicated in terms of really what the computer's doing inside. But logically, as programmers, we have an idea in our head that these memory slots we're working with are a certain size. Which size are they? Okay. So I ticked off yes for no one knows, and somewhere around 32 or 64 bits is a good bet because it's been a long time since we've been able to be certain of exactly how big a memory slot is inside our machine. Your machines are operating natively, maybe as 32-bit machines or 64-bit machines, but your programming language probably doesn't even respect that and gives you larger or even smaller logical chunks of memory. But a lot of programmers will just operate under the assumption that it's somewhere around 32 or 64 bits. And that only really matters when you're getting to the question of how much can I store in a value. So I want to show you, let's see if I can get this up without, here we go. I just want to show you what I mean by how much you can store. This is not a part of the, knowing binary stuff is not part of the course, but if we've got a single bit available to us, one slot, that slot might be a 0 or it might be a 1. So there's only 2 different values that could be stored in there, which allows us to count up to the number 1, 0 and 1. If we had 2 bits available to us, we could have 0, 0, 0, 1, 1, 0, or 1, 1. So there are 4 different combinations available to us, which lets us count up to 3, 0, 1, 2, 3. Or 1, 2, 3, 4, however you want to do it. If we have 3 bits available to us, then there are many more. Oops, I've gotten that wrong. I want 1, 0, 1, 1, 1, 0, 1, 1, 1. So I get 8 different, right? 1, 2, 3, 4, 5, 6, 7, 8. So I can count up to 8. So what this means is that if I was thinking about Booleans, I would only need 1 bit. If I was thinking about very, very small integers, I would only need 3 bits. Once I get up to 32 bits or 64 bits, I can deal with integers as big as I mostly want to. And if I've got 64 bits, then I can normally deal with longs and doubles and not have to worry. But once I get beyond something like a long or a double, there's no more space. And given that the slots are exactly the same size, whatever size that is, 32, 64, it's certainly not like 1,000 bits. Then what do we do when we're trying to store data that's bigger than just those numbers? Is what compound data is really all about. Yeah, rapid elk's on the rise. Still, I guess I could go for a shining macaw. What do I do if I need to store more than 64 bits in one place? 4 choices here. I gave you a little while longer to think about this one because, well, what are you going to do? Yeah, I missed the wombat names too. So the options I've given you are give up, as in don't try and store more than 64 bits in one place. Use as many slots as you need right next to the named one. Use some slots elsewhere and point to them. Find some magical place where I can have more memory. Or compress the data. Now, I'll give away a trick. I don't think all these answers are correct according to my Kahoot, but all these were answers people have used in the past. So it is true that there was a time in programming where you didn't try and store more than 64 bits in one place. But that was a long time. We went away from just never having more than 64 bits in one place. Cool. Use some slots to point elsewhere. I don't think that's the most logical solution, so you must have been doing some reading. The most logical solution is just to use as many slots as you need right next to the named one. But that's not what we do in reality. In reality, all we do in put in that 64-bit, 32-bit slot is just an arrow, a reference pointing off to another place, and we set aside a whole big chunk of memory in that other place for us to use however much we need is set aside over there. So the reasons why we do orange and not blue are a bit subtle. They go into how the programming works in the inside. But I'll try and give you an example later that shows up why that's necessary. But it's certainly what we do. And in the notes I just said, look, we do it this way because of stuff. And we just can't accept that. But I'll try and motivate it a bit better when we get a bit further into this. Compressing the data is an okay option, but that only works if you can compress it down to that small enough size. Processing does do that for you. It stores 3 numbers as inside the space for 1 number when it uses that special lowercase c color data type. That's a type of compression where it's compressing 3 numbers into 1. But it can only do that because it knows those numbers are between 0 and 255. So you certainly couldn't do that. You couldn't compress an array of 1,000 elements all of a sudden down just to take up the space of one. There's no magic there. Well, we'll find out what that other place is. Well, it's still in memory. There's nothing magical about it. It's just another part of memory. But it's like there's an indirection going on. It's not as not right where it might have been. Okay, questions. All right, we're done. Let's find out who answered. Who's the winner? They aren't really, they're integrated together because I signed on to Restream. Restream's going to boot me at some point for using it too much without paying, but we're using it for now. Quick buffalo, yay, all right, I'll give you that one. I mean, have I seen a buffalo or was it a bison? There was some gigantic cow-shaped thing in the Panhandle Park in San Francisco when I was there. I don't know if it was a buffalo or a bison, but they were all terribly excited about this giant animal. Every tourist thing you picked up said, go visit the whatever it is. Wasn't that exciting? Buffaloing or buffering? Ha! Too funny. I've been stuck at home so long, I'm doing bad puns. Okay. Thank you, everybody. Let's look at our topic. All right, so one thing to notice on this topic that I want to say at the start is we don't link to so many of the coding train videos, and we don't put them right at the top. And that's because in the coding train videos, which are following on with the orange textbook, that's been linked to in most of the other pages, maybe not that one, most of the other pages. See, they got the same problem. Just go. We talked about that security risk last time. So remember, we've been doing a lot of our learning out of this book, and the online text is a supplement to that book, really. If we could just point that book at you and move on, we would, but because that's focused more on a general audience and doesn't have enough of what we think of as the core CS stuff or the things that we know we need to teach in our context, we supplement it. But we're not pointing you to much on that book for compound data. And the reason is, if I look at the contents, do they have the contents somewhere? Normally you can look up the contents of a book. No, I don't see. No, it doesn't have the content. If we were to look up the contents, I should have an electronic version of it, but I didn't bring a copy of that home with me from the library, from the office. There's a topic in between functions and, well, they call it arrays, which is objects. And that's because they're introducing compound data in a different way that we had done in the past but didn't really work very well for us. And that was to introduce the idea of, fully introduce the idea of objects and classes, and then move on to arrays afterwards. And because that doesn't work well in our context, we go and learn arrays. Well, we learn a simpler form of compound data, a more fundamental form of compound data first, not worrying so much about, or not worrying at all about classes. We don't even mention the word class except for here. And then move on to arrays as an example of compound data, which means that the textbooks in that chapter started talking about objects and classes a fair bit. And the videos also talk about objects and classes a fair bit, which is not a topic we're covering. So we try to include a couple of useful videos down here, but to be aware that they might use those words objects and class, and you just kind of ignore them and move on. But that's why we got more of our own videos. One from Kim and one from Alice. And a lot more of our own text as well. So you'll find that this approach to teaching compound data, which works way better for us and our students, is not necessarily replicated in the rest of the world. So you really do want to go to these notes, I think, first, rather than search the web for things, because you'll find things are really going to start getting mixed up with topics you don't yet understand. and that we think get in the way of you learning the material. Okay. So first I'm going to introduce you to a couple of compound data values that you can think about and we can use in a processing program because we don't know of any yet. The two I want to think about are p-vector and p-image. P-vector is the one we focus on, so let's start with that. Hello, Mr. Processing. I'm sure you had a window open. Maybe not. Okay, so we're used to programs like where we're storing the xpos and the ypos, right? Easy enough. Man, the keyboard is getting so squeaky. Didn't even know they could do that. So and okay, so nothing magic here. This is just my standard ellipse that moves down the screen. Well, he's going to move diagonally across the screen. It's going to start at 0, 0. Let's be explicit about that. Or maybe not. There we go. Okay, so a circle moving diagonally across the screen because I'm using those variables xpos and ypos and updating them in the background. And each of them is taking up a single slot in memory. Maybe I'll do all of this at once instead of just introducing the types. So I've got my little diagram over here where I'm trying to, this is me trying to use the online diagramming instead of my handwriting. We'll see how that goes. Whoa, we've got a line to ourselves. We don't need that. So there's your preview of what's coming. But when I do something like an int xpos, and here's my memory over here on the right, what I'm really doing is setting aside one of the memory slots and calling it xpos. So my notation for that was to kind of name, that's the one I want. To name one of the slots, let's say I'm naming this one right here as xpos. And when I do that declaration, I actually get a value goes in there as well, doesn't it? But it's the default value. So into that slot goes the value 0. And the next thing that happens on the next line is that I'll do the exact same thing, but I'm calling it ypos. Now, because I've done another declaration, it's made another slot in memory for me somewhere. Let's say it chooses this one, and in goes the value 0 again, right? So if we ignore this line for now, when my program eventually gets down to line 11, where there's an xpos plus plus, that really means xpos equals xpos plus 1, which really means go look in the xpos slot, where there's a 0, add 1 to it to get 1, and put that back in the xpos slot. So it causes this value to turn to 1. And the same thing happens to ypos. Easy enough. Okay. And all that works because the values 0, 1, 2, 5, any of the numbers I might come up with all fit into a single slot. But there's an alternative in processing, which is quite nice. The pain point we're hitting here is that we're always having to keep track of an xpos and a ypos, and they're two different variables, but they really represent just one thing, the spot of that circle on the screen. And it becomes an even bigger problem if I want to put 5 or 6 circles on the screen. I need 5 xposes and 5 yposes, and maybe it's easy to get them mixed up. So processing gives me something that can store 2 values. In fact, it can store 3 values if we want it to, together, and that's called a p-vector. So with a p-vector, let's initialize those like we should have. I can declare a p-vector and I can initialize a p-vector, and this notation I'll talk to you about, but for now just know that that's initializing the p-vector with 0, 0. Whoa. And instead of, and that's actually storing two numbers together, not just one number, it's two numbers together. So I also have some notation to go get those numbers back out of the p vector if I want, which is the dot notation. So I can find out its first value and its second value like this. And I can even do updates on them and things like that, which is cool. So ignoring the new notation for now, I just want to show you that this is a compound data value that's doing the exact same thing as our two data values were before. So p vector is not a variable, p vector is a type. And we know it's a type because it's sitting on the left-hand side of our declaration. Declarations always go type, variable name, type, variable name. Over here the type was int, stores a single integer. Over here the type is p vector, stores 3 integers. It really stores 3, but I've only given it 2. I could give it a third one here. The point of it is it's more convenient to work with. But let's just see mechanically what that does. So here there's not a huge amount of point to it, right? Because I got the x pos and the y pos, I could just do that. But that's fine for when I just needed 2 variables. If I needed 3, 4, 5, 6, 1,000, things are going to get much worse. So we're doing all of the learning with just the 2 variable one, the very simple one, even if we're not motivated for y, and all the learning will expand to let us do things with thousands of numbers in them. Still confused? I don't want you to be confused. What's p vector? I can't be joking on that. So p vector is a new type. We know about the types: integer, character, Boolean, what else? Long and double. Those are our types that we know about. No, it's not an array type. There's no arrays here. I haven't said the word array yet. Integer, character, Boolean. Oh, the boy's out scooting. He likes to join in. Integer, character, Boolean, double, float. Those are our types that we know about. And they do slightly different things. Integer stores a small number, float stores a number with a decimal point, long stores a number with a decimal point that's even longer, double even bigger again, Boolean stores a true false value, character stores a character that we might type on the keyboard. Well, p vector is just another type, but it's one that stores 3 numbers. I'll put a third number in here just so that we know for sure. And just like storing one number was useful and storing a character was useful, sometimes storing 3 numbers is useful. So it's there. But you should just think of p vector exactly like you think of integer, except that it stores something different. Yeah? Well, the question we're going to get at here is how does it store that thing? Because it's materially different. When we were just storing characters or booleans, we could easily put them in a single slot. But we're storing 3 numbers now. How do I put that in a single slot? And later on, we're going to find some other compound data types that store thousands or tens of thousands of numbers. So how do we put them in a single slot? Well, we don't. So what's really happening with this p vector when I create it somewhere? Let's get my notes cleared up. Come on. Work with me here, computer. There we go. So when we see this line p vector pos, which is just like any other declaration, type on the left, variable on the right, then it must set aside a slot in memory and it must give it a name, because that's what we know that declarations do. So it must set aside a slot in memory, let's say this one. I'll put a circle around it just so I can see what I'm talking about. This is our slot in memory that we picked up. I don't want any fill. And it's going to call it, and it's going to call it pos. So the new slot has a name. That's all the declaration ever does. Makes a new slot, gives it a name. So that's what this one's done. I'll get rid of the circle now. So it's given this slot a name pos, and it's put the default value in it. We don't know what the default value is yet. Well, I can tell you what the default value is. The default value is something special called null that we'll talk about as we go along. So declarations on p vectors do not work like declarations on do not work exactly the same as declarations on normal variables. On normal variables, almost exactly the same, right? On a normal variable, it gave us a name, set aside a slot, and put the default value in that slot. Well, I guess it does work the same. It gives us a name, it sets aside a slot, and it puts the default value in that slot. It's just that the default value for a p-vector is something called null that we don't know anything about yet. Yeah, p-vector can only go to 3 and not more. Why is it called a p-vector? Because you can use it for mathematical computations as a vector in the mathematical sense. So you saw there was another line in my processing code that was different when I was using the p-vector. The next line was, when I did the initialization on the normal variable, I just put a number over here on the right-hand side, and that number appeared in the slot. 0 appeared over there, plus plus appeared over there. When I'm doing a p-vector, I can't just do that. I've got to give it 3 numbers, and I don't really have a nice notation for doing 3 numbers just kind of chunked next to each other. So processing gives me this new notation with the new keyword, where whenever I'm building one of these p-vectors, I have to do it not just by sticking in a number, or not just by sticking in 3 numbers. I have to use the keyword new, write down the magic incantation p-vector, and then give it the 3 numbers. But this step here is a special new step that compound data has that normal data doesn't, which is called memory allocation. So we have declaration up here, declaration just here, just as before. There is no memory allocation for a normal vector, so you can just start using it. But with a compound data, you have to do a memory allocation step, and that's this one here. So this memory allocation step, what it does is it says, you want a new p-vector in here. Okay, I better make you enough space for a p-vector, whatever that is. And the computer knows that the space it needs for a p-vector is actually 3 slots. So it goes and sets aside 3 slots. It says, all right, I've just found a place where you can put your 3 slots. Over here for your p-vector. And you want the number 0, 0, 0 in there, I can do that. 0, 0, and 0. And the last thing I'm going to do is I'm going to say, well, I'm going to make sure that your position variable actually knows where that is. And that's the magic of a compound data. The value null goes away, and instead an arrow goes in there. I need to hold some key to make this not try and... No, that's annoying. Just trying to line it up with the... Oh, nearly had it there. There we go. It says the thing that's going to go in this variable is not a number or that magical variable null that was in there before. It's now this magical thing that tells you where those 3 slots in memory are. Whoops. Okay, so that's the memory allocation step that comes with a p-vector, an extra step in the middle, and it's necessary because a p-vector is big. It's got 3 values, and later on we'll see ones that have thousands of values. But I want you to know the mechanics here, and I want you to get the mechanics sorted. The value that's stored in the slot is just a reference to the other place in memory where all of the 3 values are stored. And the reasons for doing that instead of the alternative, there is an alternative here, right? The alternative is to take these 3 and just store them all. Maybe the pos is this slot, and then 1, 2, 3 are the next slots right after. And we wouldn't need an arrow then, it'd be obvious, but that doesn't work. That falls down when you get to the next step, which we'll talk about when we get to arrays. So that's the only new mechanics we've got to learn about compound data. We've got to learn that you have to have a memory allocation step for them, and that uses this notation we're not used to yet. It uses the new keyword, and then the name of the type goes right there. So this was type p-vector, so I have to tell it that the thing I'm building is a p-vector. And then I just give it the values that are going to go in there. But once I've done that, I've got a brand new value in memory. I've got everything set up the way I need it. And I can start using it. So maybe this notation down here can be investigated now. I said that if you wanted to get one of those values out of the p-vector, you had to right, pos.x and pos.y. And the reason is that there was an extra thing that happened over here when we created the p vector. Because there's 3 slots in here, right? But they don't look like they've got names. How can I tell one from the other? Well, the p vector gives them names for us magically. Every time a p vector gets made, the first slot gets called x, the second slot gets called y, and the third slot gets called z. So now we've got names for all those slots if we want them. But just like the name for this slot was xpos, the name for this slot was ypos, the name for this slot is a little bit more complicated. Instead of just x or just y, it's actually the first name dot the second name. So to get to this value here, I have to say pos.x instead of just x. And to get to this value here, I have to say pos.y. And to get to this value here, I have to say pos.z. The reason for that is that if I want to make 2 p vectors, come on, and do the whole process again, then I'll have 2 of these chunks. And they'll also have an x, a y, and a z. So how can I tell which x and y and z I'm talking about? Well, if I give the variable name and then the name of the slot, we'll be fine. There'll be no ambiguity. So that's the mechanics of a p vector, and the mechanics of, and refer to the third number as pos.z, that's right. And the mechanics of compound data in general. Those are the new extra things we have to know. We have to know that when you first initialize it, you get a null in here instead of, that's the default value, a null. We have to know that there's a memory allocation step where a whole separate chunk of memory is set aside and given some names, and arrow gets put into our original slot, telling us where that is. And we have to know that the dot notation is how we get into the slots of that data. So we can do some more practice with p vectors, I guess, is the next thing to do. And we can draw diagrams like this all the time to follow along. I won't keep drawing diagrams though, because once we know how to draw one, we know how to draw them all, right? But if you're getting lost about what's going on in this program, then go back and draw the diagram to see what is the value in pos x, what is the value in pos y, so on and so forth. Now, I'll also, before we move on, have a look at what the debugger shows us when we're doing things like this. So we can relate the debugger back to our diagram. Do we have any questions on this diagram and what we know so far about compound data? Okay, nothing's coming through. Cool. So is p vector just take numbers and put it somewhere else? In our case, the z relates to nothing. We're not using it. The p vector is not just to put it somewhere else. The p vector is a useful tool for us in case we ever want to write our program like this. And what we're learning here is how does p vector work. Yeah, p vector can only store 3. And don't get hung up on why you might want to use p vector. It's just the simplest form of compound data. I'm going to very quickly move on to a compound data that will seem much more useful because you can't replicate it any other way. Yeah, you can hold 2 to 3. All right, let's look at the debugger. See what the debugger tells us while things are moving along. Let's put some breakpoints in and run. Oh, there's no xpos anymore because I deleted that. Okay, so the debugger stopped on line 5, which is just before we did the memory allocation. And notice what it has done. it has told us that there's a pos variable with a value of null. That's exactly what I drew before the memory allocation step, remember? When I was at p vector pos, and that's all I'd done, just the declaration, then I had a pos with a memory slot that was null. And so the debugger is showing us the same thing. If I take one step, look at that. It's updated the value to instance of something. And so instead of having an arrow off to memory, which obviously the debugger can't do, it's kind of, this is its clue that there's a arrow off to memory. Oh, and pos has grown. Look at that. I can see inside the pos if I want to. And guess what it's showing me? It's showing me there's a slot called X, a slot called Y, and a slot called Z, and they all have 0, 0, 0, just like I thought they did. It's also showing me a slot called array, which is set to null, and that's because there's more complexity in a p-vector than we're talking about here. There's more complexity in almost all of the compound data than we talk about. And that's the kind of complexity that we learn and open ourselves up to as we learn more about programming. But don't worry about that array. But we can see it's showing the same thing. It's showing, and it's also showing that, you know, X is not just out there by itself. The X is inside the pos, or the X is referenced via the pos. Okay, cool. And if I keep stepping, then I should see those values. So we draw the ellipse, we step. So we're just about to do the pos X plus plus. Guess what? The X slot of pos goes up by 1, which is this value here on our memory diagram. And then we do the Y, and then we run back around and run the program again. We didn't touch the Z, so it stays 0. We don't even use the Z, so it doesn't matter. So this is what the debugger will show you for this type of memory diagram. And you can have your preferences. These ones are certainly much easier to use when you've got things getting quite large. You can't draw out all these things when you've got 15 p vectors and stuff. But this is what happens inside the memory. There's this instance of processing core p vector means arrow pointing off somewhere. And pos.x means variable here is called pos, and there's the x. Good. I like what the debugger is showing us. So we might not have to use memory diagrams anymore, because I think we could pretty easily see that conversion between that and the debugger, right? We can just use the debugger. But we will go back to it again when we look at the next one. Let's look at another example of compound data that's maybe a bit more compelling. I need an image before I can do this, so I'm going to get one, and I'm going to save this somewhere so that I can use the image. Where are we going to put this? In my processing folder. I didn't even know I had one. Documents processing, that's fine. Okay. So I'm just going to go grab this image so that I've got one to work with. And that goes in Documents, Processing, Image Example. It doesn't go right there. It has to go in Data. I'm just trying to remember how to get processing to access an image. We don't give you examples where you have to access images. We don't ask you to write these programs, but it has to be in a data folder. But it's a good example of compound data, so I want to show it to you. I'm pretty sure you need to go into a folder called data, and we'll just call that image mq.png. See if we can make this work. Now, sorry, so over here was the p vector for the processing reference. I'm going to show you that. So it tells you what fields are available. Those are the slots inside. They call them fields. Now, these methods down here are things you can expand upon as you learn a bit more about programming. We don't do methods on compound data in Comp 1000. We do methods on compound data in Comp 1010. but we do the fields. All right, so the next compound data I want to show you is a p-image. The p-images work similarly, but slightly different. So let's do a program with a p-image. So just as before, I might need to declare it. And this time the type is a p-image. So we've already brought in two new types, p-vector and p-image. Okay, but this time, instead of drawing an ellipse, I want to draw an image. So I already know that when I declare a compound data, I set aside some memory, and that memory is null, which is not very much good to me, is it? And that I've got a second step, which is called memory allocation. So I better somehow do the memory allocation for this one. But the documentation tells me that the memory allocation for images works a little bit different. I don't need that keyword. I can use load image. So I'm going to do that and see what happens. I'll put that breakpoint on there and a debugger on to see if I can just see what's going on. Okay, so that seems to run, but the image is still null here. And then if I step, it changes it to instance of something. And then when I open it, look at all these fields. That's a lot of fields in an image. And you can, images need lots of data. There's a lot of data in there. You couldn't store that in one slot. You can't even keep track of it all. But you can think about it in terms of a diagram. So over here in my diagram, where I did, that was the same as finding another slot in memory. Let's say this one down here, pulling at img, setting it to null. That's what that step did. And then when I did img equals load image blah blah blah, that was the memory allocation. So what does memory allocation do? Well, it goes off and finds however much space it needs. Now in the case of an image, that's a lot of space. Goes off and finds however much space it needs and changes that to an arrow. And makes the arrow point to that space. And then fills that space with whatever. Now I could go through and name all the slots in this space, but guess what? That's not going to be much fun because this is a giant image. It takes up a lot of slots, way more than I've got on the diagram here. But that might show you why we want to have this memory off somewhere else, because the chunks can be gigantic. So image now is a reference pointing off to some bigger chunk of data that we can use. Now it does have fields that we can look up, but we're not going to do that with the p-image because the p-image fields are kind of all over the place. But there is something fun we can do with images, which is display them. So with the built-in operation image, we can display any image we want. So we look up the variable image to find out what's in there and ask image to draw that at 0, 0. Here we go. It's drawn the Macquarie logo for me at 0, 0. So that image obviously had a bit of stuff around the outside, empty space around the outside. PNGs have transparency, so I guess it's a transparent values all the way down until here, and then the image itself. So the image probably goes around about there, and we're done. How big can the chunks go? As big as your computer can hold. So there's no limit to them. Okay, so that's no good. Try to run your Java crash, we can do that separately, but here we go, it's working on my computer. So another type of compound data here, image, that we've worked with slightly differently, but it still has the same 3 steps, right? It still has declaration, memory allocation, and then use. Cool. Who thinks we're ready to look at a third type of compound data? I do. Okay. So these guys are built into processing, and you only really get access to them in processing. You don't get access to them in other languages. Other languages don't certainly have all kinds of compound data, but not these particular ones. There is a type of compound data that's available in absolutely every single language all the time, and that's arrays. And so most of the questions we'll ask you about compound data come via arrays, but the concepts are exactly the same as what we've seen here. So what's an array? Well, it's a bit like a p-vector, except it can store as many things as you want. That represents the top left of the image where I want it to be drawn. 0, 0. So arrays are compound data that can be as big as you want them to, and they just store, well, they can store numbers, or they can store characters, they can store anything you want. They're really flexible. They can even store other compound data if you really want. So let's do an example with arrays. We'll do the same one where I just did before with the circle moving down the screen. Now, I've called this possess because whenever I name their arrays, I name them in the plural. So this is positions. I bet I'm going to have a memory allocation in here, right? Because that's what I did with all the rest. And my program is going to want to look something like this, but instead of having a different posx and a posy, now instead of using a p-vector that stores those values for us, I'm going to use an array that stores those values. So I better learn some array syntax. But let me look at my memory diagram to think about what I want. Well, what I want is to have a slot called posses. I'm going to need some more slots here. Let's make some more space. Oh no, you went to the front. I didn't want you to go to the front. Go back to the back when you're done. You're back to the back. Good. But image moved and pos moved. Okay. He belongs. I want another space. I want something like this thing, but I'm not going to use the p-vector to do it. So I don't really need 3 slots. I only need 2. So is there a way I can get this situation? This is what I'm aiming for. I got my possess. And I want 2 slots. So let's say wherever they are, doesn't really matter. But I only want 2 of them. And I want to put 0 in each of them to start with, and I want to be able to increment that as I go. So I'm going to want this variable to somehow point at this slot in memory, yeah? So I'm going to want another one of these arrows. Pointing over here. So I know how I could do this with a p-vector, but how can I do this with an array? Well, the steps are exactly the same. I still need to declare, I still need to memory allocate, and then I can use over here, but with arrays I get a different syntax. So that's the declaration step for an array. Use 2 square brackets to say, I don't just want an integer, I want an integer array. The memory allocation is a lot like p-vector. I use the keyword new. I tell it what I want to make new of, an int array. And I tell it how many I want. 2 of them. I want 2 slots in this array. And then use is a lot like p-vector as well. I do the name, but instead of doing .x for the first slot, I do square bracket 0 for the first slot. and square bracket 1 for the second slot. So that's always the notation with arrays. It's always square bracket notation to get into a slot, and then the first slot is always numbered 0, and the second slot is always numbered 1. And then I can use those slots just like any other variable. Cool. Okay, so that is the behavior. That'll give me the code I want. I get the exact same thing running down the screen, but now I'm using an arrays to do it. So it doesn't feel like we've made much of a win here. We've learned a lot of new syntax, but what's the point? Yes, it creates a new 0 by 2 array, or sorry, 1 by 2 array. It creates this thing here, not a 2 by 2 array. Arrays only have 1 dimension for now, and so it's a 2-slot array. So I'm just going to adjust this program. Am I going to adjust this program? Yeah, I'm going to adjust this program so that I don't really need, let's say I want these to go, I want them to go across the screen. I want them to move across the screen. I don't want them to move. What do you think? No, I'll have them move down the screen. Okay. I'll have them just move down the screen, but not across. So if they're just moving down the screen, I don't need the second slot anymore, right? I can just have a single slot, and I can just use that in the X position, and the Y position can always be the same. And then I can just do this. And so now that circle is, oh, did it the wrong way around. So now that circle is always moving down. So why have I done that? Well, I've done that because now I want to put a whole pile of these circles across the screen. If I'm doing it this way, then the Y position is being stored in, yeah, exactly. So I don't think int2 would make an array with 3 variables. No, it makes it with 2 and then 0 and 1. And that's one of the tricky things about arrays that catches people up. The memory allocation tells you how many slots, and then the slots are always named from 0. So what I'm going to do here is make a 100-slot array, much longer one. And they're going to start at, now so these slots down here in the array always fill with default values just like any other variable would. So they always default to 0, right? But now that I've got 100 slots, I can do things with them. What am I going to do? Am I going to write 100 ellipse calls? No, that's a pain. If ever I want to do something 100 times, I should use a loop. That makes much more sense. And there are actually, there's a slot here for 0. Thank you. There's a slot here for 0, there's a slot here for 1, there's a slot here for 2, there's a slot here for 3, because I made this array 100 elements long. It's this guy down here, and ooh, off he goes, 100 elements off in this direction, however long it has to be. So there's a slot 0, a slot 1, a slot 2, a slot 3, a slot 4, a slot whatever. And this I is going from 0, 1, 2, 3, 4, whatever, so I could look up all those slots separately. So now I've got a loop. There's 100 different variables here, 100 different slots here. They're all set to 0 at the start, so that's not that interesting. But every one of them then has to be incremented. Sorry, every one of them then has to be used to draw, and every one of them has to be incremented. So the better way to go through 100 slots is not to have the same line 100 times, it's to have a loop that goes through those slots for us. And this is why arrays are so awesome. Because if I wanted 100 variables, the only way to, I'd have to come up with 100 names, and I'd have to have 100 lines every time I wanted to do anything to all of them. But because the slots in an array are numbered, I can use a loop to go through them all. pos0 and pos1 are variable names that I can generate during my program. So this won't actually do anything interesting because it's just going to be 100 circles all at the same spot going over each other. So let's adjust this slightly so that it's 20 plus 2 star I, which means that when I'm talking about slot 0, I'll put that at x0, and when I'm talking about slot 1, I'll put that at number 22, and when I'm talking about slot 2, that will be drawn at 24. So now I've got a lot more circles being drawn, but they're all still moving the same. Let's bump that up to 10. I think I've got the space for that. Yep. So now I'm drawing all those circles. Every one of those circles has its own variable controlling where its position is. And now I'm going to do one more thing. Instead of always incrementing them by 1, I'm going to increment them by a random amount. And I might just make this into a float. Now let's reset. So 0 to 2 will sometimes, let's go 0 to 3 and change that to integer. So that'll be 0, 1 or 2 at about 1/3 of a chance each. And that's because you're possess. All right, now we're moving. Now, so there must, see how they're all moving independently of each other now? There must be 100 different variables controlling where those guys sit. And 100 different variables being differentially updated every time the draw is run. And I can even do something like this. Reset each individual one to 0 when it gets over the height so that we can keep this running. Oh, and forget the S again. Pauses, forgetting it every time. Okay, so this is a visualization. I want you to try and see through the visualization. Every one of these ellipses is attached to a variable that's controlling its Y position. And that variable is being updated separately to all the other variables being updated. That means you've got an infinite loop. But I haven't had to make 100 different variables in my program. I haven't had to have pos 1, pos 2, pos 3, pos 4, and then pos 1 equals pos 1 plus random, pos 2 equals pos 2 plus random. That's just, ugh, that wouldn't work. But because arrays give me a nice way of naming a big chunk of slots, and each of those slots works exactly like an array, then I don't have a problem building 100 different slots and treating them all, they're all running the same code, but because there's randomness in the code, they're getting slightly different values. But the trick to making that work is to be able to allocate those 100 slots, which is what this does. It sets aside 100 slots of space for me and initializes them to 0. And also being able to process all of those slots in one go. So I'm doing that here with the for loop, and you always do it with a for loop when you're doing arrays. The slots all have a special name. The name of the first slot is poses square bracket 0, that's this guy. The name of the second slot is poses square bracket 1. This slot is poses square bracket 2, poses square bracket 3. And that gives us a loop-based scheme for naming all of those 100 slots, which means a loop-based traversal will be perfect for visiting each of those slots one by one. That's what this loop does. It starts an I at 0 and sends that I all the way up to 99 and goes up one by one. And then this line, it goes and says, I want to go visit slot number 0, because that's what I is right now, and find out what's in there and draw an ellipse based on that. Then I want to go back to slot number 0 and find out what's in it, add a random number to it, and put that in slot number 0. So I'm incrementing slot number 0. Then the last thing I want to do is check out slot number 0 to see if it's too big, and if it is, reset it to 0. Done. So it does all that once for one ellipse. It draws the ellipse, updates its position, checks if it's gone too far, sends it back to the top. Then the loop loops back around and goes, okay, now I is 1. Let's do all the same thing again. Okay, I'm going to look up slot number 1, find out what's in there, draw an ellipse based on it. Then I'm going to look up slot number 1, find out what's in there, add a random number to it, put it back in slot number 1. Then I'm going to check slot number 1, see if it's bigger than height, and if it is, I'm going to reset slot number 1 to 0. So we're running the same piece of code 100 times, and the only thing we're changing each time is which slot we're checking to do our processing. I really want you to think of pos I as just a slot in memory, just like any others, but its name is a bit more complicated to get to because it's one of these compound datas. But its name, the complex version of its name, is super useful because loops let us process over the array. Okay, questions about my code instead of just someone else's that's breaking? If you've got processing code that just freezes, shows you a gray screen or something when you run it, then it's probably because it's gotten into an infinite loop. So as an example of that, if I change that to loop as long as I is, no, that doesn't work. Loop as long as I is, right, let's change this to minus minus. Oh no, that'll break too. Anyway, infinite loops. Okay, cool. All right, so a quick recap. Now, we only just touched on arrays. What's going to happen from here is that you're going to spend a lot more time thinking specifically about arrays, and that will help to set these ideas. So really the end goal is to get to arrays so that we could learn to use arrays. They're the really useful one. But we snuck up on it by looking at some simpler compound data values so that we could learn the basics of what compound data is actually doing. And then we got to arrays, and that's the version of compound data that's going to be most useful to us. So from here and next week, we'll do, and you should do a lot more practice with arrays. And you've got a ton of questions practicing with arrays, and there's a ton of example programs you can write with arrays. And the video from Kim goes over them a fair bit too. But how do we sneak up there? Well, the first thing we did was we realized that there were types that weren't just the ones we knew about already. We've seen p-vector, p-image, and array types. Cool. Then we learned that those new types aren't atomic like the ones we know, they're compound, and that brings in something new. We learned that the main new thing it brings in is that you've got to have a memory allocation step, and here was a memory allocation step for a p-vector, here was a memory allocation step for a p-image, and here was the memory allocation step for an array. And in general, the memory allocation has a new keyword in front of it, image is special. And then once we did that, we could, if we wanted to, access the slots in that compound data. The way to access the slots in the p-vector was with a .x and a .y. The way to access the slots in the array was with the square bracket and a number. And we learned that those slots act just like normal variables. They don't do anything special once we've got the name right. So we can increment them, we can read them, we can write to them, just like we do any other slot, any other variable. They just have a different name. And they had to come into existence via this extra allocation step. So we learned a diagram for doing this looks like this, and then we have to have a reference from the actual variable slot into the larger chunk, and that the larger chunk's named normally. p-image was too complicated for us to think about the names, but the array was okay. I haven't actually put those names in. Let me do that. So on the array, this slot's called 0, and the slot next to it's called, oops, called 1, and the slot next to it, really don't like doing these things this way, is called 2, and so on and so forth. So those are the special names that array slots get. And then we learned that I mean, for these guys, you just access them whichever way you can. But for arrays, there's a cool way to access them, which is to use a loop over them. And that means we can make these as long as we want. We can make them hundreds, thousands, tens of thousands of elements long. And as long as our loop goes over the same number of times, we're good. Questions? So that's a very good one. You can get, so arrays now have a slight complexity. If I tried to access a variable that didn't exist in my other programs, the compiler would say, dude, that variable doesn't exist. You saw it a pile of times there. So let's, you know, there's no x variable, and I write x equals 4, and processing says nothing. Oh, it's still running. I write x equals 4, and processing should complain, yeah, x doesn't exist. But processing's not smart enough to keep track of, well, it can't keep track of these numbers precisely enough to know whether I'm accurately, does this pos I even exist? So I knew there was a pos 0 and a pos 1 and a pos 2 all the way through to pos 99 for this guy, because I can see that I made it 100. But what if I accidentally wrote for whatever reason? I said, go find slot number 205, please, from the pos array. Processing should stop me, right? It should say there is no pos slot number 205, just like it stopped me from using x. But it can't work that out. Fundamental in computer science is it can't possibly calculate that for me. So instead I get this runtime error where the program tries to run and then it gets to this part and it says there's no slot number 205. And the special words it used to say there's no slot number 205 is array index out of bounds exception. And that's because this guy in here, the number that we put into the square brackets is called the array index. And the bounds is 0 at the bottom, and in this case, 99 at the top. Why do we use square brackets? Well, that's the notation. That's the notation for getting into an array. This is the notation for getting into a p-vector. It just is. The notation, the parentheses, is always the notation for a function call. And posi is not a function call. Pos.x is not a function call. They're special names for variables. So we definitely don't want to use the function call syntax. Okay. So that's the basics. Now I'm going to move on to some more examples of using arrays and a few more little tricks with arrays. How do I know what value is in each of the 100 slots? Well, I know because I put them there. So just like when I declare a variable, but when in any other program, it gets its default value. When I make these 100 slots, they get their default value, and that default value is 0. I can change it after that if I want. So maybe a fun thing to do in this program might be to set them all up to something else. So I want to change every single slot number, and maybe I'll start them on a random number as well, as increment them by a random number, instead of starting them all on 0. So to do that, well, always visiting every slot in the array has to be done with a loop. There's no other way to do it, so I better make myself a loop. And it's the same loop as before. We get very used to writing this loop. And we use this variable name I all the time, short for index, and people just are used to seeing if there's an I in a loop, they know it means an array index. So you shouldn't use any other variable name unless you're doing nested loops, and then you do it. Okay. So we want to set each variable to an initial value. It's 0, but we don't want it to stay 0. Well, let's do something else. Let's make them all start from, so make the leftmost ones start at the top, but the rightmost ones start 1 pixel down, and then 1 pixel down, and then 1 pixel down. So to do that, we can just start them from, well, 0 will start at 0, 1 will start at 1, 2 will start at 2. So I can just 9, and then now they're randomly going. Yep, if you want to see what value, let's have a look what the debugger shows us, because I think the debugger is quite useful. Cecilia is right, you can just print out what's in a slot, and you would often have to do that because There's lots of them, but the debugger can help too. Let's turn our debugger on and see what it shows us for arrays. So we'll put a breakpoint in there, and off we go. So this program started up, and look, it's done the same trick as before. Good, that's what I expected, right? After I've done the declaration of a compound data, then the value inside it is null. But the next step, after I've done the memory allocation, is that it's not null anymore. But instead of writing instance of blah, 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 processing has done something a bit smarter. It's told me this is a 100-element array. But just like before, I've got to open it to see what's in all the slots. And look, processing is telling me the name of every slot and the value in every slot. Nice. It's telling me that the slots go from slot 0 to slot 99. And that always the way with arrays, if you've got an array of 100 slots, the last one is not called slot 100. It's called slot 99. And that's because the first slot is always called slot 0. We call that indexing from 0. Programmers index from 0. It's one of the things that makes us different from the rest of the world. Better, one might say, than the rest of the world. Indexing from 0 is the correct way to index. But it does cause confusion at the end. If you tried to look up slot number 100, which you might think is reasonable because there's 100 slots here, it'll give you an array index out of bounds. But we can now track this step by step because the loop is about to go through and deal with every single one of the slots one at a time. So if I step in, well, first thing to notice is that I variable just became in existence, which is what we expect. Because as soon as you do a declaration, a new slot should appear, and it does, and it gets set to 0. And we step again. Now it's stepping on here another time because it's checking the condition for us. And now it's going into that line. Now at that line, it's going to, when it's finished running this line, it will update. How did I get to? Oh, it's already done 0, sorry. It's now gone around the loop and done I equals 1. And now it's going to update slot number 1 to have value number 1. And there it is. We saw in the debugger, slot number 1 got adjusted to have value number 1. Now it's going around the loop again, so it's about to turn I to 2. Now it's ready to turn slot 2 into value 2. And so we can see it's just going one by one through this array via the loop, using the special name lookup, pos to find the slot it's interested in and changing the value in it. And it's just going to do this 100 times until every value is adjusted. It's going to catch up to us here. We're looking at the 30s. It's made it to 30, 31, 32, 33. Just going to keep doing that over and over until it's done all 100, and then it'll move on. So that's the magic with loops and arrays combining to give us all these slots and let us work on them in an efficient way. Okay, the next thing I wanted to talk about was the use of this number here. There's a trick we can do. There's a special field available on every array, which we access in a special way, which is its length. At any time, if you write pos.length, notice that it's reusing the dot syntax that we had on pvector. That will tell you the number 100, the same number that you got put in here. And so it's just a safer way to write your loops. If you write your loops from 0 to array length, you're guaranteed not to mess it up by putting 101 or 200 in there. And it's just a nice habit to get into. So this is actually the loop that we're always writing when we're doing arrays. We're always writing a loop that goes from 0 to array length, I++. And in the body, we're doing things to the array, one by one by one by one by one. Let's make this even better. So because you've got access to this I that's changing, you can write some fun programs as long as that pattern with the I works for you. So remember, in this case, we were randomly picking a number that was between 0 and 3, so that they were all randomly moving a small amount each time, and that they were kind of keeping up with each other because they were randomly in the same bounds. But what if I make the ones on the right-hand side use a bigger number? So the ones on the left-hand side, if I use the I, then it's choosing between 0 and 0 and it's never moving. And then the next one might choose between 0 and 1. Well, we'll know that'll get 0 too and never move. And the next one might choose from 0 to 2, so it maybe moves a tiny bit. And by the time we're all the way to the right, it's choosing from 0 to 100 and it's moving a lot. And because I goes from 0 to 100, I can just use I in that to get that behavior. And I've still got the debugger on, so nothing's happening. Whooshka, the ones on the right are going completely mental, and the ones on the left are going slower. I like that. Okay, so this is just fun things to do with arrays, but highlighting what's going on. So what are the things that we want to highlight that goes on with arrays? First of all, there's the notation for declaring them. And there's the notation for memory allocation. When you do that memory allocation, you tell it how long you want that array to be. And you can have an array that's 1 element, 0 elements. Even if you want, that's useless. And you can have one that's 100,000 elements. Totally up to you. Process next after it. Then to access that array, we use the notation with the square brackets, and we give a number, any number at all, that's inside the bounds of the array, which is 0 to length minus 1. Always 0 to length minus 1. But we'll often be in the habit of just accessing an array with a loop, so that it goes through every element of the array and repeats the same code, but swaps out that number for us, so that the first time it loops, it accesses the first slot, and then the second slot, and the third slot. And so we've got 2 of those loops here. And the best way to write that loop is always to use the index I equals 0, I is less than the array length, and I plus plus. And just to show you that you don't have to access things in an array, I could, for example, run this loop where I draw the ellipse and then I update the position. And then maybe afterwards I go, nah, pos 10 is special. No matter what the others are doing, I want pos 10 to stay at the middle of the screen. I'm going to change this back to the slow one. Pos S again. And you can see that even though I'm actually looping over that one, I can still access individual elements by themselves and say, now this one's special, treat him different. But I can't do that for all 100, right? I have to have 100 of these lines. But if there's something special I want to do on one of them, that's not a problem. I can still, even though I'm mostly using loops to access each element in the array, it's just a number. I can access it with that number anytime I want. Okay, so that was all I planned to talk about today. I took a bit longer than normal, that's nice. It's always good to have lots to talk about. Does anyone have any questions before I finish up? So lots to practice. You do lots of practice with arrays. And when you do the practice at the start, if you're operating on a small array, draw yourself a diagram like we've got in that to get a better idea of what's happening in memory. Just like everything else in this course, we have to do on small examples to build up our intuition and to memorize what's going on in small examples, so that when we get to big examples, our intuition can guide us without us having to draw the diagrams. Yep, so assignment stuff is for the course, so we'll talk about that on the forums. But I can briefly say, yeah, Kim did a discussion of the assignment 1 solution, which was also a chance to talk about assignment 2. And you can ask any other questions on the forums, that's fine. But we won't have a separate chat session on it, unless lots of people are asking over and over the same question, I suppose. Thank you, everybody. It's always good to have some people to semi-chat to. Okay, I'll see you all next time then.